For this project, we're going to have a larger variety of enemy types than we had in the previous project that we worked on. When creating game elements such as enemies that are varied and yet have properties in common, we shine a spotlight back to object-oriented programming and the benefits of this programming approach. Recall that OOP is quite useful when constructing or modeling class blueprints that you then intend to create instances from, often multiple instances. And OOP has all sorts of ways of maximizing code reuse through things like constructors and fields, inheritance and polymorphism, and so on. The idea is that you can use a combination of OOP principles in order to simplify your class structures and yet be able to create dramatically unique instances off of these simplified class structures with relatively little code. Now, thinking about these benefits of OOP also shines a spotlight on this sort of dual nature of Unity that I mentioned before, where you have the OOP nature of C# sort of obscured behind a somewhat non-OOP component-based interface. This component-based interface of adding scripts as components onto GameObjects, for example, is a really simple and intuitive system, but it might make you scratch your head wondering how you'd go about creating something like an enemy blueprint, with inheritance trees and such, all in code, right? Perhaps having, say, a base class for all of the common methods and properties, and then inherited classes for all the enemy variants, and then just instantiate them, preferably with a new keyword, right? Well, this lesson will go into how you could go about doing exactly that, sort of merging C#'s OOP benefits with Unity system. So as a refresher, these would be the OOP features that would make all of this work. You have constructors, which are often great for initializing the fields and properties that fundamentally describe the object, its size, speed, how it appears, and so on. You have inheritance, which is great for taking a common foundation and expanding on it rather than rewriting it all from scratch. You can, just have an enemy-based class and then a wizard and knight, for example, that inherit from it. You have polymorphism, which is great for allowing you to treat objects in code as simpler base types that they inherit from, wherever this is possible. Again, so you don't have to write a bunch of extra code just to handle cases like, if it's a knight, deal damage like this, else if it's a wizard, do it like this. Instead, with polymorphism, you can just say, I don't care if it's a knight or wizard, as long as it's an enemy, figure out what kind of enemy it is and just run its particular way of dealing damage. Things like that are the benefits of polymorphism. And you also have generics, generic classes and generic methods that let you specify a type when the method is called, or with classes when the instance is created, and thereby treat some internal detail differently depending on the type specified. So all of these OOP features are fantastic when creating video games, because a lot of game design is about creating objects and running their methods, and often objects only have slight variances between them. These slight variances should be able to be handled with the OOP toolset I just mentioned and keep your code lean in the process with a lot less repetition. And keeping your code lean is not just good for reducing repetition, it reduces the chance of an error that you're repeating over and over again, causing a really big headache as you're developing. So it's a good habit to get into. So how would one begin to think about implementing OOP enemies, for instance, within the confines of the Unity engine? Well, perhaps the most obvious way you might think to do this is to start with a class that inherits from the GameObject class, right? In order to construct your custom GameObject enemy classes and just attach the relevant components that it needs and go from there. But the GameObject class, unfortunately, is strictly sealed, meaning you can't inherit from it. So that won't work. The next approach then might be to create a prefab GameObject with all the typical components pre-attached, and then use the add component method to attach a suitable mono-behavior script that handles much of the specific behaviors of that GameObject. That approach would work, but a lot of that will seem redundant and lacking flexibility, and also might not be obvious how to initialize the object's values without a proper constructor in the mono-behavior script. Mono-behaviors don't allow constructors. I might mention this again in a moment. So before we get started on our approach, just know that there are a lot of ways to get the job done. You don't have to do it the way I'm going to show you in this lesson. Ultimately, we're doing it this way for maximum flexibility, not necessarily because it's always the most convenient approach. All right? So having said all that, on to the first step, which is creating a enemy class. But before that, let's create a new folder in our scripts folder for our enemies. Call it enemies. And I'm going to need a resources folder here in the assets folder. So call it resources. Remember, we'll be using this to load dynamically at runtime any sort of asset that we'll need. And actually, we're going to need the eyeball asset, which is going to be common to all enemies. We're going to want to load that at runtime. So you can just move this into the resources folder. So in our enemies folder, let's create an enemies script to start off with. Call it enemies.cs. So what we're going to do is we're going to have an inheritance tree of the different enemy types, all of which inherit from a basic enemy class, which will be a mono behavior. So all those inherited classes will also be mono behaviors. It's important. So these classes will end up being the main script component attached to the enemy game object that will define the enemy's properties, movement methods, damage, and so on. So it will look something like this. So we'll actually just start from scratch here. We'll say public abstract. I'll mention in a moment what that's all about. Class called enemy. And it's going to be a mono behavior. So it'll be our base class for all the other enemies that we use to inherit from it. So we'll have a bunch of enemies. I'll just show you how the inheritance structure will kind of look like to start off with. So we'll have a public class bouncer enemy type. So it's going to inherit from enemy, thereby also making it a mono behavior, as I mentioned before. We'll have a public class gigantor. And we'll have several more. I'm just showing you this for the general class structure, how this is going to look. And now we'll create a generic class that will end up instantiating with the new keyword, which will itself then create the game object that we'll want for enemy and attach a script component of our choosing. And that will determine the exact type of enemy that we want. We'll do this within the generic angled brackets, right? So we'll construct that generic class here. We'll say public class enemy of type T. This will be the script component we attach later. So we'll say where T is of type enemy. It'll have to be one of these guys, right? So when we create this generic enemy, which don't get it confused with this is a totally different class. It's going to take in an enemy, a generic enemy that'll take in an enemy. And when we create this, we'll also get a public game object. And we'll get we'll have a reference to the script component we ended up attaching. So we'll just have it here as a field. So it's going to be of type T. We don't know exactly what. Is it going to be a bouncer, a gigantor, or what other enemies we come up with? So we'll call it the script component. And then we'll have a constructor, public enemy, not the wrap group. This is going to be an enemy in our game. Wrap group shows my age right there. Okay, string name, so it's going to take in, we'll specify the name of that enemy here, which will end up showing up in the inspector. And we'll just initialize the game object in the field to a new game object with a string name we've provided. And then we'll add the script component to the game object with add component, whichever one we give it. And we'll return that reference back to the script component field so that it will be usable once we actually instantiate this elsewhere. We can access it easily through this script component field. So now let's flesh out the base enemy class that the other enemy classes inherit from. So this should basically house everything common to every enemy, basically. So our enemies are going to need a rigid body. So rigid body 2D, we'll call it body. We'll need a sprite render, call it sprite. We'll need a circle collider, 2D, because they're all eyeballs, so circle collider makes most sense. We'll call it collider. And every enemy will have a speed field as well as a direction field. And well, they're all going to need their own movement patterns. So I'll go into this a little bit more in a moment, what this means. So we'll call this protected abstract void and call it movement pattern. I'm not going to specify any details to this method. I'll mention again in a moment why that's the case. I'll mention really quickly now that protected simply, it's a accessibility modifier just like public and private. In this case, protected means that only inheriting classes that inherit from enemy can see this field. So outside classes can't see this, or sorry, in this case it's a method, right? You can do it with a field as well, make a field protected, and only the inheriting classes will see it. I'm going to have a new method here that I'm going to talk about called awake. There's nothing too difficult to wrap your head around, I promise. I'll describe exactly what awake's all about in a moment. So I'll put a little comment here, say add common components, which will relate to the fields that we just specified. So we'll say body equals, scroll this up, take the GameObject property, use add component, and attach the rigid body component. Take the sprite, and it'll hold the reference to GameObject.addComponent. Try to guess what it'll be, sprite render, right? And take the collider, the field, and that reference will point to GameObject.addComponent, the circle collider. And now another comment, I'll say set common sprite. It'll be the eyeball, right, that we will need to access through the resources.load. You can use the sprite field here, I believe, and say sprite.sprite equals resources.load of type sprite, the eyeball. We'll also want to set the collision detection mode, so we'll say body.collision detection mode equals collision detection mode 2D dot continuous. We'll also want to tag the game object, the part here, tag. So we'll want to give it the tag so we can easily reference it in code of type enemy or string enemy, but we'll be treating it that way, like we're sort of tagging it as the type that it is. And we'll also want to set it to a layer for the collision detection. So we'll need to use a layer mask and the method called name to layer. So we'll put it on the eyeball layer in the collision layer. So that would be here, right here. So here we have a method called awake, right? It's another Unity method similar to start. Actually, it's pretty much exactly the same as start. Basically, the only difference between start and awake is like the difference between update and late update, which run exactly the same way. It's just the order of execution that's different. Late update, remember, always runs after all updates have already been run, right? Well, awake is much the same in that all of the mono behavior scripts call awake first, and then calls to start follow that. So the usefulness of this is if you have a scenario where one script's start method has a reference to an outside game object, and we have no way of knowing if that outside game object's script's start method has already run. We need to be sure, though, that the outside script is in a valid state. So we can make sure of this by using awake to set that outside script's essential fields and properties, treating it more like a constructor, using awake in that way. So we're setting that script's particular state that is necessary to make it useful, to put in a valid state. While we then can use start to manage the connections between these objects, knowing that they're already in a valid state, having already run awake. So that's typically how we should be using start and awake. We really haven't had the need to do it that way, but we're at the point where problems might occur if we're not aware of this script execution order. So that's part of why I'm showing you this, but actually we're not going to use awake in exactly this context to solve any of those kinds of problems. The way that we're going to use awake here is for a bit of a different reason. We're going to use awake to set up all the common elements that will be common across all enemy types. Each enemy class will inherit this awake method, and instead each enemy class will use its own start method to set up its properties that are more specific to itself. So in a way, I'm actually kind of inverting the typical usage of awake and start like I mentioned previous, but that's okay. We're going to use it to solve this particular problem we have. All right, so continuing on with setting up our base enemy class, we have a bit of a problem that we need to solve. Each enemy's properties, or fields actually, for things like speed, direction, position, and possibly other fundamental attributes, will have to be set at instantiation. But how do we set this without a constructor, right? Mono behaviors shouldn't have constructors because, Unity is responsible for calling mono behaviors. They're out of our hands. Well, what we'll do to solve this is we'll create our own initialize method as a sort of pseudo constructor that we can run right after instantiation, because we're handling the instantiation of the generic enemy type. So then we can call the initialize method right after. I'll show you how we can do that, but first we'll have to set it up. In the base enemy class, we'll have an initialize method, and so I'll have a little comment here to remind us what this is all about. So say insert all unique values to be determined at instantiation. So it needs to be public, return void called initialize, and we'll need, again, it's a pseudo constructor, so we'll need a speed given, a direction, and a vector3 position. And we'll just say the speed field will be whatever we provide as an argument to this method. Direction will be what we provide for direction, and transform position will be the vector3 we pass in called position. All right, I'm going to call this temporarily, I'm going to put a prefix to this, a modifier of sorts called virtual, right? So we got a virtual method called initialize. So I should quickly mention what all this is about. Virtual, abstract, these little sort of prefixes or modifiers that we can add to or prepend to methods or properties for that matter, though we're not going to do that. What are they all about? Well, when we first looked at inheritance in an earlier lesson, we basically just looked at how inheriting classes just sort of silently import code from a base class, right? Well, we're going to go a bit deeper into the subtleties of inheritance by having the option of specifying a method, again, or a property as being virtual or abstract. So first, virtual. What's that all about? Well, virtual simply means that the implementation in the base class, for example, in this virtual method initialize, is the default implementation for all classes that inherit from this base class. However, those inheriting classes have the option to override this implementation with its own initialize method, effectively ignoring the base class's virtual method and instead using its own. So we have this base class enemy. So here in the bouncer class, there's a red squiggly. I'll mention what that's about in a moment. I can have public override. I'm going to override the initialize method, right? And there I press tab and it gives me the default implementation, which actually just calls the base initialize method. No real purpose for that right now. So what I could do is I could set up my own, speed equals speed plus 5, whatever. I can have my own implementation in the inheriting class, in this case, bouncer, right? So that's what you do. You override the initialize method. If I get rid of this and I don't have an initialize method, and thereby, of course, not overriding it, I just inherit this default implementation, right? Now, actually, I'm just showing you this option. I'm not necessarily going to use that, not yet anyways. We'll now move on to abstract, right? Now, abstract is a similar modifier to virtual, except that it's used to mark a method or property in a base class that must be overridden in the inheriting class. So here we're marking the movement pattern method as abstract in order to remind us when writing an inheriting class that we must have a unique movement pattern method with its own unique implementation details in the inheriting class, because presumably all enemies should have a movement pattern. They should all be unique, right? So that's also why there are no implementation details when this method is marked as abstract, because you're never accessing this method. In this case, the base class's abstract method. You always have to override it in the inheriting class. So being abstract, we just have to determine the method's name and input parameters, its signature, in other words, and then fulfill that when we create an inheriting class. So you also see that we mark the class as abstract. That's possible as well. An abstract class can have abstract and non-abstract members, as you see here, but an abstract class is never meant to be instantiated. It's sort of like a pure blueprint / base class that other classes use as a reference. So that's why we're marking the base enemy class as abstract. We're never actually going to instantiate a base enemy, right? We're going to only instantiate inheriting classes. All right, so after all this, we'll now start fleshing out our inheriting enemy classes. So starting off with what I think will be the most simplest, or one of the simplest enemy types, the bouncer type that I've come up with. So for this class, we'll want, remember we're using start to set its own particular important sort of attributes, starting point. So we'll say there's a collider field. Remember, we're inheriting that from the base class, so we'll have its radius, have the collider radius at 0.19. The local scale, so how large it is in our game, we'll say new vector 3, 1.2. And see the squiggly line, right? Bouncer does not implement inherited abstract member enemy.movement pattern, right? That was what I was talking about earlier about how it reminds us. It actually strictly enforces that we need to have, each inheriting class needs to have its own particular movement pattern. So we can set that up. So we'll say protected override void movement pattern, and get rid of that exception. We don't need to throw an exception. So we'll set the body's velocity, This will be its movement. So new vector 2 and set its direction and velocity on the y. Pass in. I'm not going to describe too much of the movement patterns because, you know, frankly, we got to kind of move along quickly and some of it may not make much sense. I just sort of hacked this out. So once we start playing the game, maybe you'll be able to pick apart how some of these movement patterns are working. Some are easier to understand than others. We'll say if body dot velocity dot y is equivalent to 0, just have it bounce. So body dot add force, pass in new vector 2, the y value of 300, and we'll call this in fixed update. All right, we're gonna just get rid of this here. Actually, we'll put this in its own file. We'll start making each script have its own, or each enemy class have its own file, just to make it easier to organize all this. So I'm gonna cut that, create a bouncer class. We're just gonna put that there. Now we're gonna test, finally, instantiation of our enemy by creating a factory script called enemies factory. So create new script. Call it enemies factory. And actually, before I move it forward, I'm going to want to have this attached to the floor game object, and that will run this when we start our game. So that's in the BG1 foreground parent here. So put that there. And here's where we'll be instantiating or creating our enemies using the code we just written. Again, we'll say void awake. We'll want to bounce our enemy, so we'll need to start off with a generic enemy of type, could be any inheriting type from the enemy class. So we'll say bouncer. We'll call this guy Bouncy Bill. And we'll say new enemy of type bouncer. And we'll pass in the name Bouncy Bill. We'll do that again. And remember, we need to access the initialize method, which we can do now through the script component. So bouncybill.script component.initialize. So this will, remember, return whatever we put in here. So we'll return the bouncer script that we attached, and we'll run its initialize method. And we'll say speed. I'm doing it slightly differently. I'll mention in a second why, or what this is all about. Direction. We'll say random.range. This will give us that random direction -1 or 1, left or right. And position is new vector 3. Well, we'll just put it at the middle of the screen. We're just testing right now. Excuse me. Sorry, these are arguments for the initialize. I actually forgot that temporarily. So, all right, so why am I using the name for the input parameters / arguments here? Speed, direction, position. Well, these are called name parameters, which is a fairly new feature of C#, I believe. And the reason I'm using it here is basically it's a handy way of telling us what these values we're inputting into the initialize method in this case, what they relate to. Otherwise, we're just dealing with seemingly, random values, unless, of course, we were to hover over the inputs and find out what the exact nature of the arguments are, what the type and the name is on the definition side of things. So just showing you how name parameters are available to you. You can get rid of these and it'll be working just like any other method that you've used before with just the values input. But I think this is a little bit easier to understand what's going on as we're creating our enemies. All right, so now let's run this and make sure that's being instantiated correctly in our game. Let's wait and see if Bouncy Bill comes into existence. All right, we got 2 of them because we already have a cloned floor, right? Because of our tiling script, right? But that's okay because every time we're gonna tile a new floor game object, we're gonna spawn new enemies. So we'll do that in the next lesson. We'll worry about it then. So great job powering through this lesson. We'll continue fleshing out enemies in the next lesson.